Welcome. In this question, we are supposed to find the current flowing through the load ZL. There's a lot of ambiguity around this question. This question is actually from GATE 2018 instrumentation paper. So let's try solving this question logically. Now, the first thing that comes to your mind when seeing an op amp is applying virtual short. So uh, so if we apply virtual short, we will get the voltage at the non-inverting terminal is 2 volts. So if we apply that logic, the voltage on the inverting terminal also will be 2 volts, and the voltage here will be 2 volts. Now the here is 5 volts, here is 2 volts, so some current will be flowing in this direction, and by the basic equations of the BJT, we can find the relation between the collector current and the emitter current, which we are supposed to actually find. So that approach will be completely wrong, as we are directly assuming that the op amp is in negative feedback. Also, there is a lot of misconception around the op amp also, that if the feedback terminal is the feedback loop is through the inverting terminal, the op amp will definitely be in the negative feedback. That's actually not the case. It depends on how the feedback circuit, what the feedback circuit also consists of. So uh, the most logical way, the conceptually correct way would be first identifying that if it's in really in the positive feedback, or is it in the negative feedback. So uh, positive feedback and negative feedback are referred back to the control systems. So let's start from there only. So we have some input V in. We are talking about voltage, so let's take the voltage as V in. We have a summer block. V in is added, and the feedback loop which is coming through here. There is a amplifier. The amplifier in the question, it's a BJT, any amplifier. It's like a black box, and here we have output. We are taking some feedback, passing through some feedback loop, which reduces the gain to beta. It's the gain of the feedback loop is beta. Now we also know the Barkhausen's criteria, and let's not go so deep. Let's just um, write the equations. So the voltage which will come here is, so here will be beta times V naught. The voltage which will come here is V in minus beta V naught, and it will go into this amplifier which has a gain A. Now for a negative feedback, which certainly is here, what will happen if the output is increasing? So we know that the main thing of negative feedback is stabilizing the output. So how does it stabilize? So if the output is increasing, what will it do? So if the output is increasing, the feedback loops gain will increase. So beta is constant, beta times V naught. If V naught increases, beta V naught as a whole increases. Now because the input is constant, we need a constant network. So input is constant, and V in minus beta V naught. So if beta V naught is beta V output increases, beta V naught increases. If beta V naught increases, this whole term, let's call it VT. Okay, so V in minus some, this was previously some, let's assume its value to be 5, and V in to be 10. So 10 minus 5 was 5. Now V naught increases, so beta V naught increases to 6. So 10 minus 6 is 4. So the input which is going into the amplifier actually decreases. This means the output is actually decreasing. So because the output is decreasing, once again it will go into the feedback loop. It was previously 4. The beta V naught term is decreasing. This term VT term will increase, and hence it will act like a bang bang control. Okay, so in control systems there's different types of controls, PID, bang bang. Okay, so this is a bang bang control type of thing. And uh, so the basic idea of negative feedback is whenever the output tries to increase, the feedback loop will stabilize and will bring down V naught, and when V naught tries to decrease, it will do the opposite action, which means increasing it. So this loop continues, and the output kind of remains the kind of remains to a constant value. The average value is a constant value. Now let's apply the same logic in this op amp also. So uh, let's think the op amp as a differential amplifier. Assuming the op amp has a differential gain of AD, so the differential voltage will be the inverting terminal non-inverting terminal voltage minus the inverting terminal voltage. In this case, it's AD times the non-inverting terminals voltage is 2 volts minus inverting terminals voltage. Let's take it V. So V. Okay. So what let's assume that the output voltage, the output of the op amp is increasing. So if it increases, the BJT, the voltage increases, and hence the current through the base increases. When the base current increases, by the basic operation of BJT, the collector current also will increase. Assuming they have given the transistor to be ideal, and as the transistor is ideal, we we are also given beta. So we can infer from that the BJT is operating in linear region, that is as an amplifier. So when the BJT is operating in linear region, we can apply the relation, that is IC equals beta times IB, and by this relation the collector current will increase by beta times when the base current is increasing. So eventually the collector current will increase. When the collector current will increase, the voltage drop here, so more drop will be across this 10 kilo ohms resistor. It's actually 10.5 kilo ohms. So the voltage drop across this resistor will be more. When the voltage drop will be more, the voltage here will eventually decrease. When the voltage here will decrease, the let's what will happen to the op amp? When the voltage V decreases, the differential voltage actually increases. So 2 minus a smaller value will result in a much larger value. Hence the output will further increase, further decreasing the value. So in this scenario, the operation of negative feedback is not coming into play. That is, when the output increases, the feedback loops should stabilize and decrease the input. But in here, when the output increases, the feedback loop um, uh, increases the output much more, driving it into the op amp will drive into the saturation voltage. So it's like a positive feedback loop, and hence we can conclude that the op amp is in actually in the positive feedback. So when the op amp is in positive feedback, we know that either the op amp's voltage will be plus V saturation, the generally it's 15 volts, or it will be minus 15 volts, that is negative V saturation voltage. So by this we can see that the op amp's voltage will be either plus Vsat or minus Vsat. Now so yeah, so let's assume the op amp's voltage to be, so the output voltage of the op amp is, let's suppose, plus Vsat. Okay, so if it's plus Vsat, what will happen is um, when it's plus Vsat, the BJT will be turned on, and the current will be flowing through the 10 kilo ohms resistor. So we actually don't know what's the actual current flowing through this. So because we don't know the current flowing through this, there is actually no way to verify that if it's actually in the plus Vsat region. So because we don't have a way to verify if it's in plus Vsat, let's assume to be in minus Vsat. Okay, so if we assume the BJT to be in minus Vsat, this means the BJT there is no current flowing through the BJT, which means it's turned off. So the current will be zero. When the current will be zero, the total 5 volts will appear across it, and because it's in because there is no feedback loop here, so it will act like a normal differential amplifier. And because the voltage at the inverting terminal is higher, the output will obviously be minus Vsat. So this analogy of the assumption of the op amp being in minus Vsat is valid. Like it's actually there is no contradicting statement that is arising from the analysis, so we can happily assume that the op amp is in minus Vsat rather in plus Vsat, because we don't have um, uh, any way of verifying that the op amp the BJT is in plus the on state or off state. So minus Vsat, uh, when analyzing the circuit, assuming in it is the op amp is in minus Vsat, the circuit behaves very correctly and are there is no contradicting statements. Hence we can state that the BJT is in off condition and the load is floating, hence no current will be flowing through it. Hence the answer will be 0 amps.